So for standard 6.1, I'll be doing a question from the book on chapter 6. I'll be doing question 6.7, and it asks us, consider a right circular cylinder of radius r, which I've drawn over here. Find the equation given the angle as a function of z for the shortest path on the cylinder between two points with cylindrical polar coordinates. So these are the 2 points that I have chosen, these two, and they're represented over here with these 2 points. And it further asks us to describe the describe the properties of the shortest path, or the geodesic, or whether it's unique, and also by imagining the surface of the cylinder unwrapped and laid out flat, explain why the geodesic has the form it does. So first thing that I did was to figure out the distance formula of this length. And I'm well aware of the Cartesian form of the distance formula. It can be represented in this way. And if I want to take the partial derivative of this, or the partial distance, I can just convert that equation to this. Now moving from here to here is a bit tricky. What I had to realize is that since the radius is not changing, so it's going to be on the surface, I figured if I were to look at this image from a z point of view, so if z was actually this way, I would just see an arc length of this. So I realized this is just an arc length for the cylinder. So to rewrite, I can rewrite an arc length. The equation of arc length is r times theta, and to find the partial of it, because we know that the angle is changed, you can rewrite it as this. So dx and dy dx squared and dy squared can be represented with this new equation that we have over here. So moving on, so what I did next is just I divided it through by dz squared, and that's why, and I have this final equation over here. The next thing that I did was figure out the path length of it, and to do that, I just used this formula. What you get to, once you get to this point, you finally realize that to take the integral of this is going to be very hard and tricky. So we use the Lagrange equation, which I've written over here, where this is our f. In terms of r, theta, and what's the last term, and z. So this is our f. And once you do that, I just plug it back in. So the first equation, and the first part of the equation just tells us to differentiate this in terms of y. However, we don't have a y in our form, but we do have a theta, which is changing, because that's one of the points that is changing. So you're going to derive f in terms of theta and minus dx. Again, our dx is changing, however, it's not changing. This is going to change to be dz, which is I've presented over there, and dy prime of that can be rewritten. We're not going to write dy prime, we're writing the angle prime of that in the z direction. And what that really means is that this means just this term over here. So I don't want to rewrite that at the bottom. So we have our equation set up. What I've noticed, the first thing that I noticed is that this goes to 0 because we don't have a theta in this equation. So that goes to 0. Then we're left with this equation, and now when you differentiate this equation, holding everything constant except for this part, you get this. This is your new answer. We differentiate that, you get over there. So you still have the dz in front of the negative. The negative does disappear if you just multiply each side by a negative. So the negative will go away. And rewriting this equation, we get it to be at this point. So my next step from here to here, what I did is I integrated each side in terms of dz. And once I integrated, I got rid of this term over here, of this d over dz, and then negative, I just moved it over to the 0, and that cancels out. And when you integrate 0, you get a constant. So that was what I was left with. And then from then on, I just try to get my d angle over dz to one side. And you can follow my work through and how I got that. So I move on until I got to this point where I got it to one side, and this is the equation that I was left with. I move this to the other side, and I squared everything. And once you got to this point over here, I just took the r's, because this is r to the fourth and r to the second. So what I did is I factored out an r to the second, r squared, and that came out. And over here I use integration by part. So I just realized this is separable. So I just integrated. I just moved the dz to the other side and I integrated. And this is the equation that will represent the shortest path in terms of the angle. Now, the question further asks us to elaborate or to talk about the path length and what it really means and some of the properties. So for that, we have this page. So what I really notice is that the equation that we have, theta is, or the angle is unique to a specific path. And what I really mean about that is that if I were to start over here, there isn't any other short path. That's the only path that I have. This means even if theta was just theta equals 2 pi plus another theta, I would still get a different answer. Even though I'll be at the same point theoretically, because I could just go once. I could do more loops and still end up at 2, but I'll still thing is I'll have a different path. So that's how theta is unique. And we also know that the path, the circuit is also could be seen as the intersection of the cylinder and a plane. And the way you can picture is that the plane will be coming in at an angle to the cylinder, and then that will create the arc path. And for the last question, when it asks us, imagine the cylinder kind of unwrapped and laid out flat, and explain the path, the shortest path. Why is it in that form? Well, when you unwrap it, you realize that it's actually a straight line, which kind of reiterates what I said in the beginning, that this is unique, and that for 2 points, it only is one way to, or there's only one short path. So this kind of proves that this is the shortest path. Thank you.